Welcome everyone back, and thank you for showing up for our talk today on some basic building science. I've offered several different, we'll call it versions of this, but what I wanted to talk about is primarily what we see here on this very first opening slide. As we can see here, a number of different conditions, inspection photographs taken at various stages. And if we take a look at it, what I really am going to be talking about is certainly a little bit of building science coupled with some common sense issues that inspectors might encounter in the field. And often people question, why take a look at building science? And really, building science is really about analyzing the house as a system. That acronym up there, HAAS. And we want to talk a little bit about indoor air quality and certainly the issue about the importance to ventilate, or in other words, ventilation. If we take a look at the house as a system, it begins with mutually dependent elements, issues such as the location, the climate, the home construction techniques that have been used, and even the materials. As we can see here, some fairly common materials are present in all of these photographs. But we can see that these are the end result of some of the conditions over time that this house or homes, all these homes have basically gone through. And there's probably a good reason for all of these. So what we want to do is talk about old homes perform different than new homes, certainly. But for the so-called average home, how do you really know how tight or leaky the structure is? Simply even just with this visual type of inspection. So in most cases, we really don't know. I've inspected virtually thousands of homes, and I love collecting the photographs of the conditions to show people this is what can happen. And this is a good reason, perhaps, of explaining why it happens is the building science part of it. So you really don't know, even from some of these obvious clues, what's really going on other than looking at things and doing a little bit of research of why does this happen. But the key for building science is really about taking a closer look at why the conditions look like this and why they occur. And it's also equally as important to understand what is the impact on the people, the occupants that live in homes such as this. So just a little bit of an outline here. I'm going to talk a little bit, obviously, about what is building science. And if we take a look at it even from the basic point of view, we want to talk about the house as a system. We're going to talk about heat flow, airflow, and moisture flow. These are the three primary mechanisms that we really want to look at when we talk about building science. What is actually happening within the inside of this house, or what they call the building envelope? How does it have an impact on the indoor air quality? So again, what are some of the issues with sources, possibly the symptoms, and let's take a brief look at the solutions. The last grouping here is on ventilation. So why do we need to ventilate? And why is ventilation of a house very important? And what are some of the systems? And of course, maybe some of you already are familiar with some of this, but certainly ventilation is another critical part of building science. And we're going to talk a little bit about combustion spillage and also on the topic of radon. Now, on the topic of radon, we're doing actually another separate webinar specifically addressing radon. I'm going to touch on it very, very lightly and very briefly. But I just wanted to kind of give you a general idea about the webinar. Will focus on these performance and strategies concerning and regarding the control of heat, air, and moisture flow. These are the biggies. So again, what is building science? As we can see here in this slide, it indicates that it involves the study of building materials. And it's just not building materials itself, it's the interaction, including the study of building components, building details, and the methods of construction. consists of really taking a detailed look at the interaction between the variables such as the impact of temperature, air, water, and moisture in the interaction of these various systems, often referred to, we'll call it in the profession as the building physics or building dynamics. If we take a very, very quick look, we can see in the lower left some conditions of a knee wall. This is the exterior wall, a foundation wall of a house, slightly above grade. We can see behind what was covered with fiberglass insulation in a vapor barrier, we can see moisture has penetrated into the inside of the structure. It also means that it's also starting to create the damage of not just to the wood, but to potentially going to have an impact on the indoor air quality within this house. By the way, this is a fairly new construction, a fairly new build we're looking at. So it's not just old buildings and old homes that have issues. Sometimes the way we build new homes can be problematic too. In the middle is me holding a baggie full of basically insulation that was used as an attic access cover. So it's basically a sheet of drywall with a vapor barrier with a whole bunch of that insulation stuffed into it. And what's really, really hard to see, because I would really have to blow this up, is a lot of condensation, moisture, water inside of that baggie. Well, really think about this as also kind of really our house. So when we think about, the finishing of what happens in walls and ceilings, in construction in general, certainly houses need to breathe in a certain degree. And that's where the ventilation issue kind of fits in. The last image there over on the right is me holding up a little bit of, we'll call it the wall covering, okay, the air barrier. And if we take a look along that concrete block wall, which is a concrete block foundation wall, in the sill plate, we can see some shims because the foundation's out of level, but there's big, huge air gaps left there for air to leak inside the house. So again, all of these kind of give us a little bit of a background on, why do we look at things and why do we need to look at it in detail? So again, we're going to talk about the house as a system. So your insulation, heating, cooling, windows, doors, the ventilation of the exterior walls, the foundations, and even the siding operate in a linked interactive system with each other. As builders, quite often they don't think that way. And as architectural detailers and construction experts, you want to look at it with a different set of eyes and with a different set of knowledge. So if we start taking a look at it, as I mentioned, these things are all interrelated. So if I swap out the old windows for new windows, there will be an impact, a change in the house. And likewise, even with an insulated metal door versus the old wood door, and so on. So how do these things impact what's going on with the house, but also more importantly, what's inside the house? So what we want to do is take a look at some of those linkages and what is happening. And as we can see here, the house is based on the holistic value of studying the house in relationship, not just to the material I'm putting on as siding, but the whole house as a system, as it indicates here. So we can see here components within a house that can have an overall effect is the external environment, certainly wind, rain, snow, and dust, and snow, so on. Do we have occupants? Certainly the number of occupants within a home can have a dramatic impact of the condition within the house. As we know, as we add more people, we're adding potentially more moisture, but also thinking about pets or other things that are, we'll call it our favorites. Like me, I have a basement with an aquarium in it. That's a moisture generator. Well, it also helps to maybe increase a little bit of relative humidity in the dry winter, but it's not so great during the summer. How about the building envelope? I mentioned about the building envelope, the foundation, and all the system, that outer skin of the building, so to speak. How is it well constructed, or is it well constructed? And the connection points, especially when we talk about areas such as the sill plate and all those different details tying it together. Appliances and equipment also have an impact, along with mechanical and electrical systems. Again, when we talk about the house as a system, we start looking at if it's out of balance, it can cause problems. So for example, let's say concerns about high energy consumption seems to be the biggie nowadays. But what about wood rot and mold and drafts, or perhaps even combustion spillage? And certainly in most homes, the development of and recognition of condensation buildup within the house. So the interaction of all these components, protection from the external environment, links with external services such as water and sewers, those connections, the quality of even the internal environment, and the durability of the house and its systems, and not to even forget the fact the durability of the materials that actually create the outer skin of protection for the people inside the building. And of course, capital and operating costs, heating and cooling costs, the cost of even just turning on the lights, so to speak. And of course, the other thing that we need to think about is how about ongoing maintenance for the longevity? We can see here in this image, why seal the leaks at all? Well, building codes today, National Building Code, and most every provincial building code talk about sealing the house up so it becomes more energy efficient. We also need to look at it through kind of the analogy, or maybe through the view of, really, are we creating the house to be a bag and moisture gets trapped in it? How do we get the moisture out of it so we don't have these issues and problems? Well, I mentioned that we were also going to talk about heat, air, and moisture flow. Well, the answer to how do we get rid of air leakage and what are some of the issues, we can see the answer, the interaction of these affect the indoor air quality. So we can see in this little illustration here, the air pressure, for example, the winds, air leakage, we already talked about, the solar impact, certainly the climatic conditions, temperature, both indoors and outdoors, when we think the difference between summer temperatures and winter temperatures, and vapor pressures. Excuse me. When we talk about the building science part of it, we talk about these flow principles. So what we need to understand that heat flows from hot to cold. So again, if we use this analogy, in the winter, hot to cold, we heat the indoor space and the heat wants to escape towards the outside. Is it through the walls, through the foundation system, the floor system, or up through the attic? When you think about air and water, moves from high pressure to low pressure. So again, we see in this little illustration here, the differences in air pressure. So the wind can create a pressure on a house. Is it going to be a positive or a negative pressure? And we also know that moisture migrates from wet to dry. So for example, again, we take a look at this, moisture traveling through the building envelope. And we're going to take a look at that in a little more detail shortly. Really, I'm not trying to turn you into building science specialists, but what I think we need to talk about is a few basic science principles that do apply, which really are presented on this slide. We often hear that heat rises, and that is true. But often what we really don't realize is that when heat rises, it also escapes through those external, we'll call it cracks, crevices, and air leakage points within the building envelope from a number of different locations. Uncontrolled air leakage through the building envelope is most often cause of the housing performance issues and problems, such as development into mold. Again, let's take a look at this next slide, heat, air, and moisture flow. The interactions of these affect the indoor air quality. If we take a look at the illustration off to the side for a moment, we can see in this cross-section representing a floor framing in a wall, just kind of a partial section of a wall, we can see the summer and winter conditions. The accumulation of moisture, warm moist air and cool air on the inside in the summer, and condensation occurring within the external wall itself. Now, mind you, this illustration does not show a finished siding on it, but it's just for illustration purposes. If we take a look at it in the winter, well, look where the position of that moisture and condensation accumulates towards the outside, okay? Because we also have heated air trying to escape to that cooler surface, which we talked about earlier. So those flow mechanisms. So again, some recommendations, as we can see here on this slide. We can see increasing the insulation levels in the exterior walls, floors, and ceiling systems, reducing the interior moisture condensation, thus reducing mold, incorporating a well-sealed continuous air barrier. That's what we saw earlier when I was holding up that basically, we'll call it air barrier system on the outside of the house that was under construction. In indoor air pollution, we have to think about it the best remedied by simply identifying the source and controlling it at the source. In operation of continuous mechanical ventilation systems such as a furnace fan, heat RV, so heat recovery ventilation or energy recovery ventilation system, or simply even just something like a bathroom fan. Again, an airtight building needs to breathe. And nowadays with new builds, as I mentioned, the codes require that we build tighter, and certainly we'll call it with less air leakage in a home. So many of these can be readily controlled right from the new build stage if we think about that. But however, how do we do this when we are dealing with an older existing house? That becomes a different problem. Excuse me. Let's take a look at some heat, air, and moisture flow conditions. We start with the upper left, we can see an attic. And in this attic, if we take a look at it, we have some nice fluffy, newer blow-in insulation. But what we also see is some darkening of the back of the plywood sheathing for the roof up in this attic space. Well, again, to me as an inspector, this is visible signs of moisture accumulation and condensation. And if we really take a look at it, the insulation is blown all the way over to the, we'll call it sort of the edge of the roof, the lower edge of the roof, which means there's lack of air movement for proper ventilation to reduce moisture buildup in an attic space. If we kind of jump down to the left, we can see a sill plate and a rim joist. So the sill plate is sitting on top of a poured concrete foundation wall. The sill plate is that upper, we'll call it wood framing that the floor joists tie into. And what we're looking at is we're inside of a basement looking towards the outside of the exterior wall. And the builder has put some nice fiberglass insulation in. And you can see I've removed a piece of the vapor barrier, so the plastic vapor barrier. But what we can see behind there is that white stuff. And that white stuff is really frost. Moisture has come in from the outside. Because this is a winter condition, we have warmer air in the basement. We have cold temperatures outside. We can see the movement of moisture that has frozen inside of the house in this particular instance. Over time, we can see that it's starting to darken even the plywood sheathing on the floor system. Over time, if it remains moist, we're going to have rotted wood floor joists, or potentially even a rotted wood sill. Again, not uncommon things that do occur, but again, an explanation of why do we take a look at building science? You know, why do these things happen? Again, upper right, we can see a slide that I indicated, or photo I showed earlier. Again, moisture penetration into a knee wall. Again, that insulation has been removed. The vapor barrier has been opened up to take away and basically look at the condition of the water damage being created to the sheathing board on the outside wall of this foundation. Of course, another way of looking at it is just going beyond our eyes and using technical tools, such as a thermal imaging or infrared camera. Take a look at the comparison of these two specific locations. So we can see here, if we take a look at the little oval in blue and the arrow indicating and take a look at the thermal imaging view of it, of that same window, using a thermal imaging camera, we can see not only is there a temperature difference, that little temperature scale bar off on the left-hand side, we see there's a difference in temperature occurring at the wood framing. And also, if we take a look at the dark blue spots, we start to see probably not just what we would call cold air gaps, but also the transmission of potentially water accumulation and moisture within this wall system. By the way, we're looking at an exterior wall because obviously when we have a window, we don't get to see these things. It looks pretty good to the right. Does this area look wet? Not really. You cannot see this with the naked eye. So again, in some cases, we need to use, we'll call it more elaborate tools to really define what's going on those walls. Another thing I want to talk about is what they call the neutral pressure plane. The neutral pressure plane is directly related to what's known as the stack effect. And again, I apologize for some of these, we'll call it building science or more technical terms. But basically, as we know, hot air rises. And as the hot air rises, if there's potential areas of leakage, that air is pulled up, or we'll call it the cold air, or we don't know what type of condition that air is, but it wants to basically pull in the air from outside of the house through these open joints, and we'll call it air leakage locations within the house. It occurs where there's no pressure difference between the inside and the outside, and the location is determined by the amount of air leakage in the location. So if we take a look at the little illustration in the lower right corner, we can see I've indicated with a blue arrow sort of that, we'll call it the lower part. Usually basements and crawl spaces tend to be cooler. Above, we're trying to heat a space or keep it comfortable. And we can see all these arrows indicating potential heat trying to be driven out towards the outside, especially in colder climate areas. But one of the largest areas it's going to try and penetrate through is up through the ceiling, because as we know, heat rises. So this is what is known as the stack effect. So it drives the heat loss through air leakage, hence stratification and air leakage. As we know, as we stand on a floor in the winter, it tends to be maybe a little cooler around our ankles than perhaps around our head or towards the upper part of our body. So again, as this air is trying to be pushed out through different cracks and crevices, even within the ceiling, okay? Or, as I mentioned, through air leakage points. By the way, those air leakage points could even be the electrical outlets on the outside wall, along the baseboard, at the floor. So those are all potential air leakage spots. So again, this is what stack effect is all about. Next, I'm going to talk a little bit about air quality. So when we talk about air quality refers to the condition of the air around us. But more importantly, certainly outside is important, but certainly the quality of the air indoors is important. And people often say, well, why? Well, if we think about it, with this cooler weather and colder weather facing us shortly, we're going to be indoors a lot more than we were over the summer or during those nice milder days. So this becomes an important issue. Okay, so on the lower portion of the slide, we will see a list of factors that impact the air quality. So without air exchange, a home can accumulate moisture and mold, as I've been sort of talking about, and become a problem, and you can experience simply poor air quality. So a few of the causes could be poor ventilation, so lack of fresh air coming into the house, problems controlling the temperature, too high a humidity, thus potentially dampness or mold, development of mold, conditions that impact fresh air incoming the house. So is it being restricted? How about airborne chemicals potentially within the house? VOCs, cleaning products, solvents, and so on. Or perhaps even allergens. And again, there's more to the list, but just to kind of give you some quick general examples. When we start talking about IAQ, indoor air quality, how do we evaluate? What are some of the methods of evaluation when we look at the indoor air quality. Again, as an inspector, quite often entering into a home, you have to trust your sense of smell. So you start looking at, does the house smell musty? Okay, so when we take a look at this, as I indicate, ventilation plays an important part of indoor air quality. What does the area in your house really smell like? And I'm not trying to get personal, but is it fresh, or does it smell of mildew? Perhaps just musty, or perhaps even moldy smelling. Even smelling a bit of mildew, mildew provides a hint that the mold is present. Ventilation is a combination process which results in supply and removal of the air. So what we want to do is we want to have an exchange of air, get rid of the, we'll call it stale, moist, moldy stuff or mildewy smelling stuff, and introduce fresh air into the house. So if we start taking a look at condensation, can be a sign of high humidity. If we look at the heating system, potentially there could be areas where we have to deal with carbon monoxide. And of course, some of those side effects could be nausea, dizziness, shortness of breath. Worst case, carbon monoxide poisoning could equal, even at worst case, unfortunately, death. So there are a wide range of tools that can measure indoor air quality. I'm not going to get into them because that could be a whole separate issue by itself, a whole separate webinar. But for example, there are sensors that measure, as you can see here, carbon monoxide, the particulate matter, VOCs, volatile organic compounds, humidity, formaldehyde, radon, and so on. But best, hire a professional indoor air quality investigator is what I would recommend. But certainly you can trust your sense of smell right from the get-go, which probably is a good sign of further review of concern is required. So how do we control moisture and pollutants? Well, a few things we need to think about. There are many ways to control moisture in a home and also outside of the home. So for example, cleaning and repairing gutters. Gutters that leak can be potentially water that can come down the siding, and potentially if there are cracks or a lack of sealing, enter into that wall structure, the exterior wall structure, and cause damage. Eventually, not just condensation and water entry, but potentially mold. Again, outside, does the ground slope away from the foundation? We want to get the water away from the foundation wall. We don't want it near the house, so to speak. And of course, fix any leaks in any types of seepage areas that's possibly encountered. Put a plastic cover over dirt in a crawl space. I've been in many crawl spaces where it's simply just dirt. Well, simply putting down a full one single layer of just a plastic vapor barrier, and even holding it down with some bricks or something, some heavier material, will help reduce that rising moisture dampness coming up into the house. Use exhaust fans to remove moisture, and certainly the old standby, even prior to things like heat recovery ventilators and so on, is simply an exhaust fan to remove moisture. Isn't that what we should be doing in any bathroom, or perhaps even any kitchen, or actually in any moisture generating area, including potentially even the laundry room? We want to keep indoor humidity low. We want to use dehumidifiers. And again, as an inspector, often if there was a lot of, we'll call it mildew moisture issues, I would recommend to my clients perhaps the use of a dehumidifier to knock down the relative humidity or humidity buildup in a house. Raise the temperature of the cold surfaces where moisture condenses. Again, one of the most common areas that we think about when we look at the cold surface issues is simply look at windows in the winter or in the change of seasons. We can see that those cold surfaces often will be telltale signs of moisture buildup within the house. And certainly proper venting of appliances that produce moisture is important also. Moisture problems and their solutions differ from one climate to another. So as I mentioned, there are many different ways of controlling moisture and certainly pollutants in a house. So let's talk a little bit about the ventilation. So the ventilation, we'll call it component now. Good ventilation is basically essential. It removes contaminated air and is going to replace it with fresh air. It reduces humidity in a home. It's best to have controlled ventilation for energy efficiency rather than having air leakage. Perhaps the building code people were onto something when they started about sealing up our homes a little bit tighter. It wasn't just about making our homes just energy efficient, but certainly there are other ways of getting energy efficiency within a house, but it also included about adding ventilation. So there's many types of ventilation systems out there. So again, we can see here in these two photographs, the sort of that darkish development of condensation eventually is going to turn into mold. And we can see the presence of this in this particular photographs. So let's talk a little bit briefly about the types of ventilation systems that are out there. We can see there are three primary ones, what's known as a natural or passive system, such as your window or door. The spot ventilation, which again, as an example, is simply something like your bathroom exhaust fan. Or how about a whole house fan? Actually, it's the preferred best for improved indoor air quality. So we can have it either through exhaust, a supply, a balanced air system for both in and out, so it's known as a balanced system, or by or through a heat energy recovery system. In the lower slides, we can see in photograph one, a newer construction, simply windows. And again, getting back to passive natural, do they operate? Do they open? Again, just natural ventilation through a window and or through a door. Well, typically we don't leave our doors open all the time, only for short periods of time, but certainly windows are well designed and generally equipped to provide passive natural ventilation. Again, the spot ventilation, that slide in the middle, new construction, this is the installation, okay, at the rough-in stage of a bathroom fan. So that basically the ductwork and the housing up in the ceiling. And the third one, the third slide is just, by the way, that's my HRV in my house. I was cleaning it and I took a photograph of my heat recovery ventilation system. And again, it's great for heat recovery, but that baby runs pretty much a fair amount of time most of the year. It's providing fresh air and it's also exchanging the old stale air out of the house. So I have controlled ventilation. I want to make sure that my house isn't going to be developing into a moldy, musty state. Let's talk next about a little bit about combustion spillage. What is combustion spillage and why is it important to indoor air quality? Well, combustion spillage gets back to carbon monoxide buildup potentially in a house. So if we take a look at it, when we talk about the building envelope, we need proper and safe discharge of any fuel burning products of combustion. And you can see I provide a little bit of a list there. Normally, these combustion products, which can include both visible smoke and various invisible gases, are vented to the outdoors through a chimney or some type of vent pipe. Some people call those the flue. Unfortunately, they may on occasion escape or back up into your house, where they could raise a variety of health and certainly other concerns. As I mentioned, carbon monoxide could potentially kill in the worst case of scenarios or make people very, very sick. Annual inspection and certainly periodic maintenance, to me, is very critical for all combustion appliances to ensure proper venting. If we take a look at it, combustion spillage is a term for unwanted flow of combustion gases coming back into a home. Often we refer to this as what's known as backdrafting. So problems can include chimney or vent problems, equipment problems, or pressure problems. Pressure problems is when we have, for example, high winds and the flue gases are trying to rise naturally up through this flue pipe. Again, remember, when we heat something like water or the furnace, we want those flue gases to go up that, we'll call it chimney or vent pipe. We can see here where they're depicting a smoke pencil being used to see if it actually is going up the chimney or perhaps coming back towards us. So again, just used as an example here. What are some of the signs of combustion spillage? Well, backdrafting due to house depressurization is often probable cause of combustion spillage. Typically, some of the things I would look for is, for example, if we were to show you a picture of a hot water tank, I look for signs of little metal, we'll call it, looks like little pellets or dust sitting on top of the water heater. Signs that backdrafting has occurred. Sometimes even with furnace equipment, we can see that in the forced air heating equipment as being part of the air that was pushed back in, combustion spillage, which was supposed to be flue gases. They should have went up, but came back. Of course, some of the things we need to think about is watch for warning signs such as, again, from a personal point of view, headache, skin, throat irritations, shortness of breath, or impaired motor function. Are there any strange combustion odors anywhere in the house? Is it hot and muggy air around the heating equipment? Are there soot stains around the combustion appliances, that I mentioned earlier, or melted plastic fittings at the top of the domestic water heater? So again, this depressurization can cause a powerful exhaust fan or even weak chimney vents and wind downdrafts. Again, the hot gases have to rise through the flue and exit the home because they're not as dense as indoor air. The pressure differential that allows for the release of these combustion gases can be overcome by usually low indoor air pressure caused by high rate of expulsion into the outdoor through exhaust fans, fireplaces, and dryers. So there are specific or certain types of appliances within the house. For example, in our house, we have a what they call the Gen Air cooktop. It has a very powerful fan on it. And it can, in some homes, under certain conditions, cause backdrafting just by putting that Gen Air cooktop on. So in other words, the old way it used to snuff out the pilot light on the water heater. So again, signs that problems are brewing. One of the last topics I want to talk about here is about radon. The topic of radon is really not a new topic. It's actually a very old topic, but it is certainly starting to come back into light again. So again, concern in Canada about indoor radon levels began actually in the 1970s. Some homes and communities where uranium ore was either mined or processed were found to have elevated radon concentrations, but they are not exclusively the only communities. I want to use a couple of examples in my area. My area, that's southwestern Ontario, I live in the city of Windsor, or just outside the city of Windsor. It's possible to see the readings of 99, it's called becquerels per cubic meter. Well, not too far away from me is a small town called Amherstburg, Ontario. It's within about 30 miles or less, and it has significantly higher levels of 150. So 99, well, I'll round it off to 100. A little bit down the road is 150. But let's talk about perhaps where John lives in Ottawa. I'm not going to get into the numbers, but it indicates basically that over 1 in 4 homes have higher radon levels than the safety guidelines of 200. So again, you can see if you're tested your home and the radon level is above the Canadian guideline of 200, Health Canada recommends that you take action to lower that level. There are various ways of testing, by the way, for radon. Basically, the longer term are going to give you the better results. Again, back in the day, I used to do some radon testing, but in my area, it wasn't a popular add-on service that people were willing to pay for. And it really isn't that overall expensive, especially when you consider the health and safety of your family. So again,
yeah.
Go ahead, John.
Yeah, so according to my radon measure, I am at 181, which is, and it says my long-term average is 232, but that number moves by just breathing on it a lot, right? So So my long term is 181. So it's just under the 200. So, and for me, I think it's coming. So I have two sub pumps. One I sealed with rubber. Another one I sealed, but I'm gonna have to recaulk it. I was told I didn't do it. Rudy lectured me on sealing it. I need to redo it a little bit. But my house, I also have a lot of cracks in my floor. I have what's called dead concrete. It's old, right? 1928. I don't know if my floor is that old. I think they might have put it in later, let's say 1930s, 1940s. But I have a lot of, visual cracks. And so if I pour water, they seep through these cracks. Now, I can't see the dirt, but I'm sure radon is pushing up because of the pressure. So, so Rudy suggested, as how many of you know through our webinars, that I have to do is a V grinder, grind it out, and then refill the cracks, or get an air exchanger to remove it. So I'm looking at, possibly both, because I live in my basement, like I work, this is where I am, like 90% of my day. So I'm trying to address it. If it was much higher, I probably by this time would have holes in my foundation. The problem, my foundation, they're about 2 feet thick. It's called rubble pour foundations. So it's all the boulders that they put together with basically some type of mortar and sand, which is disintegrated. So I need to get a professional person with a water drill and drill through my foundation. I don't want to take a chance on it. So that's my radon update.
Thanks, John. Good to know. And as we mentioned, we will be having another certainly webinar in more detail on the radon issue. Again, maybe just to follow up a little bit on the radon mitigation, what John was talking about, there are techniques for reducing indoor radon levels, certainly what's known as mitigation. And they range simply from sealing the radon entry points, cracks in the foundation, gaps around the sump pump, etc., to increasing the overall ventilation in a house. But if you're getting into the higher range, and certainly this becomes critical, installing an active soil depressurization system is really the way to go. That it's going to actively draw the radon out from under the house or around the foundation system and basically vent it to the outside. Basically, that's what that illustration is supposed to indicate. Okay, so we see, again, the radon at the bottom foundation area, the ducting and tubing, the radon fan, and basically it being vented out through the top of the house or through the roof system. So this is how can we deal with the radon sort of response. So again, sub-slab depressurization is the most effective and reliable reduction technique. It's also the most common method that's used by the CNRPP certified professionals. Again, just kind of a little bit of a quick plug. There's a little bit of information for follow-up there, as we can see on the bottom of the slide. So again, the PVC pipe collects the gases, it's piped upwards, it's depressurized, and the venting basically forces the radon out of the house. And that's what you would need to do if you're in one of those areas where it is a serious concern. Again, a few more details to kind of follow up on it. Again, we can see here kind of an older illustration, floor wall joint cracks along the connection between the footing, the floor slab, and the foundation wall. Any cracks or crevices, like John was mentioning, perhaps around a sump pit or any other drain that might exist. And there's obvious other areas where it could get into. So it would need a good review to basically take a look at where all these little cracks and flaws, potential entry points occur. If we take a look at over to the right-hand side, what I call detail A, it really is, this is what is recommended for new construction. So when a new house is built without doing actual radon testing, quite often the building codes in Canada now require what's called a rough-in. So this is what we have here is a footing, a concrete floor, and we have this rough-in PVC piping that's capped, okay, potentially for future use if radon tends to be high in an area. So we can see basically that's the requirement for new construction. Of course, if we start taking a look at B, certainly it could be vented out through the sidewall, probably ideally up through the roof system. And we can see that in all cases, there's a specific radon exhaust fan that is used to basically draw out the radon out of the house, or from, I guess, within the house, and certainly from its source, which is primarily in the ground. Okay, so let's kind of start to look at a summary here. So what basically, building science may not be your expertise when it comes to diagnosing and considering the relationship of the house as a system. So there are unseen conditions beyond the general recognition of even simply the visual inspection. So even the inspectors in the field generally are always trying to do a good job, but there are certain things when it comes to building science that some people cannot quite explain exactly why things are happening. But certainly through the looking at the house as a system and how things are interrelated helps drive the clues of an ever, we'll call it researching part of building science of why things like this do happen. So the key point is to build the home so that structure stays dry no matter how wet the weather or how many long steamy showers even the people inside take, or how much cooking anybody wants to do. A lot of older homes did that on their own naturally because they had a lot of air leakage, lack of insulation, and so on. So builders and designers could get by without much knowledge of the actual building science. However, today, this is no longer the case. We can see that, again, if we look at the visual physical evidence I've shown you in some of those photographs, water stains, surface warping, evidence of building component failure, those things are on their way to certainly causing problems within the house. These are serious hidden problems. Today, infrared thermal imaging, again, as I illustrated in that one photograph, has become essential for improving building diagnostics, as well as even more specialized testing. For example, when diagnosing air infiltration or exfiltration, problem areas can be isolated in preparation for repair work, even through things, something like a simple blower door test. Where do the air leaks occur? Similarly, pockets of moisture or wetness in a building envelope can be identified so the source and extent of the problem can be addressed. We saw that in cases up in the attic, or in those, again, those photographs, where a little bit of insulation was removed because people were concerned about, we'll say, a little bit of issues such as mold developing on their drywall. So when we take a look at it, some final thoughts, and again, some reference links. When building any building, it requires careful consideration of the entire whole building system. In particular, sealing up a house or any building can be a good thing, but what steps have been taken to minimize the potential consequences or perhaps the misunderstandings of the living environment and the impact on the people that are living in that house? So even understanding even some of the basic concepts of building science helps deliver an overwhelming improvement in the health, safety, and durability of our house, and certainly for longevity too. So what we want to think about is the way and the details put into housing. Again, the reference links provided here provide excellent up-to-date information on the topics. CMHC has one on moisture and air penetration, or air issues rather. And another great reference is one, he's sort of the guru of building science, his company's Building Science Corp, and he has a whole series of building science videos. Again, one of our other guest speakers up and coming, Gord, will also be providing some great reference materials. Again, I look forward to any questions you may have or any comments that may have been posted.
Jean-Alexandre mentioned that in Quebec, they actually have an arrangement with the Lung Association for test kits for $45. And I know that in the Quebec as well, they have a radon gas initiative taking place too, because it's some of the communities are extremely high areas. And I also want to mention that as part of our Indigenous Building Knowledge Exchange, we have a radon gas program for communities that are about to build for free. We will look at their blueprints to make sure that their risk mitigation strategies are built right in. Many communities that we know of are building unaware of the radon gas in the communities. And when they build, they don't have the piping and proper mitigation strategies built in. Because if you build them at the beginning, it's not much. It's like $1,000, maybe $2,000 at best. But once you build the house, and then you realize there's radon gas, and you can only tell if you got radons when you build it, but you can assume by testing other areas, your proximity, if you have high radon. Once the house is built, the cost for mitigation are a lot more. How much more? I don't know. It depends what you do, but it's like $5,000, $6,000, $7,000. So it's best to build in advance. And we're actually launching a brochure called, building, to be smart, you need to build radon resistant homes. So just assume you have it and build accordingly. Don't think around, maybe not, you have it. Just assume you have it. And that way you take all the precautions.
Well, that's good. Good to know. I see Elvis has posted it. Indoor Air Plus program through EPA is also a good program. Again, I've looked at their information. Go ahead, Elvis.
Yeah, I was just going through that program not too long ago, so sounds pretty interesting to me. And it has a lot of good features with dealing with housing issues, especially on the indoor air quality side. And I kind of wish that we would have it on this side, really, But I'm going to check into that a little bit more and go from there.
Well,
You raise a good point, Elvis, because I just don't know the EPA stuff. Like I've referenced the EPA stuff on my research on radon gas. Again, I'm not the expert on this, so I'm learning. But what I'm being told is that the Canadian requirements are much more stringent than the EPA.
Yeah, that's what I hear too. So
Yeah, but what I like about the EPA stuff is that it's explained well, right? It's very simple, it's easy to understand, and so I know, like, on the radon gas issue, that's what we're in the throes. As a matter of fact, we're in the throes of redesigning a couple of Health Canada's radon gas brochures because they just don't make any sense, especially for First Nations communities.
yeah, okay.
So
That's why I see that First Nations communities, since we are like North American citizens, I guess, Native people, so we have access to both borders. And I don't know about that part of trying to get some assistance through them if they would kind of like honorary Canadian citizens too, especially on the North American Indian part.
yeah.
I can really haven't really questioned that so much, so,
Mhm.
but I will pretty soon, sometime.
Yeah,
know,
no, I think the lots of the information out there, we need to reposition it, especially for a lot of the indigenous communities, because there's a high concentration of, overcrowding, the
Yeah.
addictions, right? The addictions collectively, including smoking, right? And so they all impact the indoor air quality, right? And then
Yeah.
when something like breaks, like a bathroom fan, and we know that boiling, meat and products is a cooking, way of cooking for a lot of the indigenous communities, and that also creates a lot of moistures and indoor quality. So I think there's an opportunity to reposition a lot of this stuff and that's what we're trying to do for radon, because it's such a high killer. It's a silent killer.
I know we did some radon testing here, maybe about a year or two ago, and one house had like a high Barkel, it's like over 1,000, and
Oh,
the other house didn't have like less than 200, and the other house had about 800, and it varies, right, from one lot to another lot.
correct. That's right. And that's the challenge with radon gas.
Yeah,
So what we're suggesting is you just build assuming you have it. Like just build, because if you build and you build with all the mitigations and you have it, well, that's fine. Like, it happens. Radon gas actually is worldwide. It's just not a Canadian thing. It's heavy in the European countries, more or less where hard shields are, right? So around the world, radon gas is a huge issue. But if you build to it, it's not an issue. It's like it's nothing.
when you look at the maps, like radon maps and all that, I think every province has really like a high content of radon.
Yeah, yeah. Yeah, and a lot of the indigenous communities are located in really high areas. Like I
Yeah,
said, even, I have to tell you, when I took on this project, because sure, I'll test to see what this is all about, and all of a sudden, like beam me in, Scotty, I was having some cases up to 240, and I had it near my sub pump, and up to 275, right? Okay, well, that's a high number. So,
yeah, it is.
yeah, and again, Colin has another topic on radon gas, specifically targeting mitigation, which I think is critical. We need to plan better, build better to address stuff like radon.
Yeah, but a lot of those mitigations they could be quite costly.
Not if you build at the very beginning. My understanding, if you're building a new home and you put radon gas mitigations strategy in front, it's only a few $100s. It's piping. You put in special pipes that you seal. But if you build a home that had radon gas, then it could cost you thousands of dollars. You have to drill into the foundation and relieve the pressure. Then you have to put these vacuums to suck it out, and then you have to push it out. And again, Colin will give us more of an understanding of that, but it's better to build it than to retrofit.
Just saying,
Again,
okay.
right? So,
I'm just saying it could be pretty pricey.
exactly.
Yeah.
Okay.
Well, you guys did a good job today.
Yeah, Claude, as usual, very informative.
Yeah.
Well, thank you. One of the spin-off comments I was going to give also is there's that whole we'll say knowledge base also on basic indoor air quality. Years ago, as we know, or some of us that are in the know understand or remember that CMAC used to have a program out specifically for training of indoor air quality.
Yeah, I
So
did that in 2003.
yeah, they pretty much abandoned the program, and basically they licensed it out to, we'll call it
Yeah.
various contractors to deliver. So it still is out there, but it's not, we'll call it the free version like CMHC used to offer. But again, another important topic that ties into not just building science, but let's say, the air quality in any home, both on and off reserve. Certainly, air quality is a big issue of, hey, you want healthy air that you want to breathe in your house.
I know their protocol was at that time, I don't know if it still exists or not. Maybe they have changed it a little bit. I'm not sure about that. It's that when you do a IAQ investigation, you have to know your building science, and because they don't allow instruments like measurement instruments like for VOCs or any kind of chemicals, right, that's in your home. They don't take those measurements. They rely on investigators to know their building science and to report it as reported in your report to the homeowner or the chief and council.
I think the strategy is we're pushing, the importance of need to know, but we're also trying to overcome the strategy of we don't want to know. And that's our challenge, right? So anyway, all right. So our next one is on Thursday. And is that right? No, it's a holiday. It is Indigenous Day.
Oh yeah?
Yes. There you go. I have to remind everybody.
I didn't know that. I didn't know that one.
Well, there you go. It takes a non-native guy to tell you it's your holiday.
Yeah, I think it was originally slated for me again with the technical guide update.
Yes.
But hey, we can forego it for a while.
Yeah. So I believe that's right. I think Thursday is a holiday, but if not, we're here.
All right. Isn't the holiday Friday the 30th?
I think you could be right. Is it the 30th or is it the 30th or 29th?
No, well, the National Day of Truth and Reconciliation is Friday.
It is
September 30th.
I just seeing here, what do we have? Do we mess up on our planning again?
Okay, I've got September the 29th technical guide on northern housing, the update.
Correct.
Yeah.
That's
so
right.
We're not going to have another one until next week?
No, we're on for Thursday.
Oh, you're going to have on Thursday?
Yes.
Okay.
Thank you.
Okay.
And then Friday's the holiday. And that's right. I know why we were thinking Thursday, because some were taking Thursday off.
Oh.
As well for some family stuff. So that's why, that's right. My notes are that we decided to do it, but others were planning to take Thursday off as well. So, okay. All right. We are here on Thursday. Terrific.
Okay.
All right. Thanks, everyone.